So here is something interesting for you folks to chew on. Like, did you folks know that it takes significantly more amount of time to copy data from memory to CPU than the actual processing time on CPU in modern data analytics? And this is like a foundational bottleneck on processing. And the technologies like Velox, which is doing efficient CPU execution using vectorized engine, are not only like an incremental improvement, but they are a new way of doing the processing. They are a new thought in this era, and they do a significantly improvement in the processing. So I'm Abhishek, I'm from Google, and I'll be talking about why we integrated Velox-based technology in Dataproc, the challenges that we faced, how we solved that in Dataproc, and what are the production scale challenges that we faced at Google, and some of the performance improvements that we did as part of this journey. So where is this magic happening of Velox and Gluten in Google Cloud? So it's all happening in Google Dataproc. And think of Dataproc as Google Cloud's fully managed and scalable service, which allows customers to run open source data processing frameworks like Spark, Trino, Hive, Flink, etc. It takes care of cluster lifecycle, cluster creation, scaling, security, monitoring, while customers can focus on their real workloads while leveraging the open source APIs and tools which they are comfortable with. So customers don't have to worry about entire cluster management. That is all taken care by Dataproc. So we are seeing a sheer increase in data processing demand from our customers. It is not only growing, it is growing exponentially year over year. The amount of data processed by customers has grown by up to 5x in last couple of years. And with this introduction and adoption of AI and ML workloads, the kind of innovations that we are seeing in AI and ML space, this demand is further going to grow in the future. Now, on the one side, we have this rocket ship demand of data processing. I would like to present a counter viewpoint that the raw processor that is responsible for actually doing the data processing, which is like CPU, their performance is kind of plateauing out now. The era that was defined by the Moore's law, where we were seeing exponential growth in hardware performance year over year, is kind of coming to an end. Previously, we used to see approximately 20% performance improvements year over year just by hardware improvements. So that free lunch is kind of over, and we have to do something new to kind of get the performance improvement for our customers. And what does it mean for our customers? So we have an increasing demand for our customers, and they want to keep the infrastructure cost as a fixed percentage of their revenue. They don't want their infra cost to increase exponentially with their data processing demands. So cost is a constraint within which customers operate. And since previously they were able to increase the data they used to process exponentially just because of the hardware innovation, and that no longer holds true, so we have to now think about newer levers of innovation. And for that, we have two paths. So one thing that we have realized is this is an era of building efficient hardwares and building hardware that is more focused for data processing world. And there are lots of companies working in this space. So one path for us is to leverage accelerators for meeting the customer requirements. And then there's another second viable path is to build efficient software. And intelligent and efficient software is the need of this hour. And Velox-like libraries are built to squeeze out maximum performance from each cycle of the CPUs. So we decided to integrate Velox and both GPUs in our Dataproc offering. And last year, we launched Dataproc Premium. which supports integrated GPUs, as well as Velox and Gluten-based execution in Spark. As of today, there are 10,000 of jobs from the customers running every day on Dataproc Premium, which is backed by Velox and Gluten. So we are able to run Velox and Gluten at scale in real production environments for our customers. And what does our customers see with this integration? So our customers are seeing approximately 3x better performance for their Spark workloads because of three areas of improvement that we did in our Dataproc Spark offering. One is like we integrated it with Velox. Second is we did lots of I/O optimizations. And third is like we have our own query optimizer, which is derived from some of the Google's other engines' query optimizations. So customers are now able to process way more data at the same cost and at a higher pace at Dataproc. So doing a deep dive into what this architecture looks like, how did we productionize it into production for Dataproc? So we built this architecture composed of different building blocks. And we support multiple engines, like Spark and Ray right now, but we are planning to support Reno and Flink in future. And we have this intelligence layer that decides whether we should use Velox or GPU-based execution or the normal engine for the execution of the workloads. We have our own custom optimizer that is based on the hooks connected with the Spark optimizer. So we re-optimize the plan that is generated by Spark's Catalyst optimizer. Then we have our own caching layer on top, which caches like hot data on the local SSDs within the clusters. And we are building our own layers for materialized views and indices, which can be used to reduce the amount of data scanned. Then we support multiple storage connectors. The primary ones are GCS and BigQuery connectors, because around more than 90% of our customer workloads accesses these storage connectors. But we also support like Bigtable and Spanner connectors, because some percentage of our customer workload uses that. And the architecture has been built using the building blocks so that it becomes a lot easier for us to support newer open source engines in an efficient way on Dataproc in a faster way. Talking about Velox, after the integration of the Velox, when customers actually started trying it out, they faced different kinds of issues. And I'm going to categorize them into three major pillars where we worked on. The first one is the performance. So when customers started onboarding on Velox-based execution, some of the customer workloads started seeing the regressions. And when we did a deep analysis of those regressions, we found some patterns. The first pattern was workloads which have high number of broadcast hash joins started seeing regressions as compared to normal Spark performance. Then the second pattern was when there were consecutive joins. In those cases also, we saw some regressions in customer workloads. So I'll be talking in deep about some of these optimizations that we did at Dataproc to solve some of these problems. Then another area where we invested a lot into is after integrating Velox-based execution, we started seeing that the bottleneck shifted from execution to scans. And lots of our customers' workloads were slowed down because of the slower scans. So we improved the I/O connector that is used for accessing the GCS. And then we also added support for new data sources, including BigQuery native tables and BigQuery iceberg tables. BigQuery is one of the primary engines used at Google Cloud. And lots of our customers use BigQuery storage. So increasing the scope of Velox to these data sources was crucial for our customer adoption. Then the third thing that we focused on is how to increase adoption of this technology. There's always resistance for customers to adopt anything new. Specifically, Velox as an engine is evolving. They were always worried about the correctness of the results. And they didn't want to do the testing or trying out at their end. They wanted a simplified way from the Dataproc so that they can simply onboard on it and we take care of choosing the correct technology for execution behind the scenes. So that's where we developed this intelligence layer that has this automated qualification. So it figures out whether this workload is suitable for pushing down to the Velox-based engines, and it automatically pushes it down to the native or Velox-based engine for subsequent runs. Then we also developed a technique for automated validations. So customers can opt into it, and what it allows is to have some percentage of your workloads and some stages of that workload would be tried with both Velox-based execution as well as Spark-based execution, and the results would be validated at the end, so that customers can be very confident about the correctness of the results. Because in some cases, as Binway also talked about in his talk, there were some semantic incompatibilities between how Spark behaves and Velox behaves, so customers were worried about those semantic incompatibilities. So let's double-click on what we did for broadcast joins. So when we analyzed, like, a majority of the Dataproc workloads in real-world scenarios have broadcast joins. And at Dataproc, we don't have a fixed threshold for broadcast joins, as there is in open source Spark. So open source Spark has a fixed threshold of 10 MB for broadcast joins. But in Dataproc, we do historical analysis of the event files. And based on the driver and executor memory, and based on the historical analysis, we adapt the broadcast hash join thresholds. So what does it mean is, like, the actual value of broadcast hash join threshold could be way more than 10 MB. Now, for open source Spark, the way broadcast hash join works is like they broadcast hash tables directly from the driver. So the hash table is built only once in the driver, and then all the tasks use the already built hash tables. But in the open source integration of Velox with Spark, this driver was just broadcasting the raw data, and hash table was built at each task again and again. So this created an overhead, specifically if the broadcast hash join threshold is high. So each task was recreating this hash tables every time, and that causes like issues or delays in our customer workloads. So what we ended up doing is building a caching in executors, and we build hash table once in the executor, and then each task basically uses that hash table instead of building that hash table again and again. So we effectively reduce the number of times this hash table is being built from O of number of tasks to O of number of executors. And that way, we were able to help our customers migrate most of their workloads or unblock their workloads to migrate to Velox. Then another problem that we saw is, like, with the significant improvements in the execution, the task scheduling and serialization became a major overhead. The guiding principle for distributed engines is that your task scheduling and serialization should be around 5% of overall task runtime. But since with introduction of Velox, the execution improved significantly, this task scheduling and serialization overhead became more than 30 to 40% in our customer workloads. So to solve this problem, we introduced something called adaptive split computation in Dataproc's offering. And what it does is, like, it adaptively coalesces multiple splits into bigger splits and then gives it to the execution engine. So that increases the executor efficiency at our level, because now executors are not waiting for the tasks, and they have big tasks to work on. Along with that, it also helped in reduction of scan operations, because for each split, we have to do some metadata operations, and GCS as a storage or any remote file system storage is not optimized for small size scans. So this adaptive split computation helped us in improving both scan performance as well as effective utilization of executors. Then, as I talked earlier, 18% of Dataproc serverless workloads processes data on BigQuery storage. And we added support for BigQuery storage BigQuery Iceberg tables as well as BigQuery native tables in Velox. And how does it operate is basically driver gets the metadata of the table, and then it calls the create read session API on BigQuery storage, which gives the read streams to the driver. And you can think of read streams as Spark partitions. So we serialize the read streams and pass it on to the executors. Now we implemented an arrow-based read streams API in BigQuery storage API. So when executors uses these read stream APIs to read data from BigQuery storage, they directly get it in arrow. And now this arrow can directly be consumed by BigQuery connector. So since Velox is directly consuming the arrow file format, we avoided this whole conversion of formats, and that helped us in building a very efficient BigQuery storage connector for Velox. And similarly, we implemented the write flow for BigQuery storage connector in Velox. So here, driver basically creates a temporary table or the destination table using the BigQuery API. And then executors keep on writing data directly in arrow format to BigQuery storage. Upon the completion of the data writing, executor sends, or the task sends a commit message to the driver, which contains the commit ID. Once driver receives the commit IDs from all the tasks, driver calls a batch commit API on the storage to finalize the table creation. Now, in case of insert overwrite, driver also takes care of cleaning up the destination table if required. So with these two, with the introduction of BigQuery storage connector in Velox, we were able to open up Velox for even more customers than before. Now, talking about GCS connector, which is the primary data source for Google Cloud customers. So we found out scan is the biggest bottleneck. In fact, from the morning we have discussed this. With computations becoming more effective, the bottlenecks are kind of shifting towards scan, right? So we implemented a connector which is based on the gRPC to reduce the number of network hops that we have on the path of the scan. So gRPC is like a high-performance open-source library that is used to interact with cloud storage. So as you can see here, by default, the traffic goes through multiple hops, that is via GFEs and different servers, and then it reaches the cloud storage backend. So that limits the throughput that we see, as well as it introduces the latencies in terms of TTFP. So we developed this direct connectivity part to cloud storage that avoids this inter-between layers. And right now, it uses simple gRPC APIs. But in future, we are planning to move to BiDi APIs of gRPC. And that will further avoid the network latencies and can give us a very higher throughput than we typically see. So as you can see here, if we use the typical JSON APIs, though the initial startup time is less, but the time for subsequent reads is way higher than the gRPC ones. With gRPC APIs, if you use it for long-range reads, it gives you subsequent performance improvements. On our C++-based connector, we saw 50% reduction in P50 latencies with this gRPC-based connector. And the last thing that we developed at our end is the intelligence layer. So customers can focus on their workload, while intelligence layer takes care of finding the best way to execute their workloads. And as part of this, we store all the Spark event files, historical event files of our customers at our backend. And we have a background service that keeps on running, that keeps on analyzing those event files and generates insights from it. The insights could be of very different natures. The simpler insights could be what should be the memory configurations that are required to run these jobs, what should be the broadcast hash join thresholds. But now we have developed analyzers that can decide what is the best execution engine for these jobs, whether this job should be pushed down to the Velox-based engine or GPU accelerators, or should run on Spark. So this insights, so I'll double click on this analyzer, which makes this decision of whether this job can be pushed down to native or not in this talk. So we start with the raw plan on the left side, and then we have a node visitor, which marks which all operators are supported by Velox. And this could be like a very simple logic, whether this operator is supported in Velox or not. But in some cases, we have developed a complex logic, like what is the schema of it, whether we have correctness results for that schema or not. So for example, initially, we were facing some issues with timestamp data types. So those timestamp data types were excluded in terms of supported operators. And it has like more complex logic, like for broadcast hash joins, what is the size of the left side, and whether we should push it down or not. So after this visitor, it identifies the nodes which can be pushed down to the Velox. But then we found that if we break the whole stage code gen boundaries of Spark and we push down to Velox, it doesn't help with the performance. So we implemented another visitor that takes the output of the first visitor and makes sure that if a single node is not supported within the whole stage code gen boundary, we mark that entire whole stage code gen as not supported. And then later on, we implemented a cost analysis function on top of it that suggests whether this whole workload can be pushed down to Velox, or we should use normal Spark engine for this workload. Yeah, that's all I had. Thank you for your time.